Before the middle of the 20th century, aviation advanced in careful, incremental steps. Aircraft designers relied on wind tunnels, mathematical models, and operational experience gathered slowly over years of service. This method worked well as long as airplanes remained within familiar aerodynamic regimes. But as jet propulsion matured and engineers pushed aircraft towards supersonic speeds and extreme altitudes, that traditional approach began to break down. The air itself behaved differently. Shockwaves formed where none had existed before. Control surfaces lost effectiveness. Pilots reported violent oscillations, sudden pitch changes, and mysterious losses of control that could not be explained with existing theory. The gap between what engineers believed they understood and what aircraft were actually doing in flight grew dangerously wide. In the aftermath of World War II, the United States faced a strategic reality shaped by speed, altitude, and technological dominance. The Cold War demanded aircraft that could fly faster than adversaries, climb higher than enemy defenses, and explore flight regimes no nation had mastered. Yet every attempt to simply extrapolate existing designs led to unacceptable risk. Conventional aircraft were optimized for known conditions, not for the unknown. Engineers recognized that a new approach was required, one that treated uncertainty not as a liability, but as the central purpose of the aircraft itself. The airplane would no longer be merely a weapon or a transport. It would become an experiment. This necessity gave rise to a revolutionary idea. Aircraft built not to serve an immediate operational role, but to answer fundamental questions about flight. These machines would deliberately enter dangerous and poorly understood regions of the flight envelope. They would fly higher, faster, and more aggressively than any aircraft before them, gathering data that could not be obtained in laboratories or simulations. Out of this philosophy emerged a lineage of experimental aircraft that would come to be known as the X-planes. At the heart of this effort was a partnership between the National Advisory Committee for Aeronautics, later transformed into the National Aeronautics and Space Administration and the United States military. Their shared objective was not short-term performance, but long-term knowledge. The desert skies above what is now Edwards Air Force Base became an open-air laboratory. Vast, empty expanses provided room for error, emergency landings, and the inevitable failures that accompany true innovation. In this environment, engineers and pilots accepted a simple truth: progress would demand risk and sometimes sacrifice. The earliest X-planes were born into a world where breaking the sound barrier was still considered by many to be physically impossible. As aircraft approached Mach 1, shockwaves formed over wings and control surfaces, producing violent buffeting and control reversal. Pilots described the experience as hitting an invisible wall. Traditional aerodynamic theory offered no reliable solutions. The Bell X, one was conceived as a flying bullet, its shape dictated not by convention but by ballistic research. Its rocket engine, its thin wings, and its compact fuselage represented a radical departure from existing aircraft designs. When the X-1 finally shattered the sound barrier in level flight, it did more than achieve a milestone. It validated an entirely new way of thinking about aircraft design. Supersonic flight was not a dead end, it was a doorway. The data collected during that program reshaped wing profiles, control strategies, and structural design across the aviation industry. Commercial airliners, military fighters, and later spacecraft would all benefit from the lessons learned during those dangerous early flights. As speeds increased, altitude became the next frontier. Conventional aircraft struggled as the atmosphere thinned. Engines lost efficiency, control surfaces became sluggish, and the margin between controlled flight and stall narrowed to razor-thin limits. The X-15 program emerged to confront these challenges head-on. Powered by a rocket engine capable of producing enormous thrust, the X-15 was designed to reach the edge of space, where aerodynamic flight blended into orbital mechanics. The X-15 was not merely an aircraft, it was a bridge between aviation and astronautics. Its pilots experienced hypersonic speeds and altitudes above 300,000 feet, conditions previously encountered only by ballistic missiles. At such extremes, aerodynamic heating became a dominant factor. The aircraft's skin glowed under thermal stress, forcing engineers to develop new materials, insulation techniques, and structural concepts. These innovations would later prove essential for spacecraft re-entry vehicles and high-speed military aircraft. Equally transformative was the human element. X-plane pilots operated in environments where reaction time, situational awareness, and decision-making were tested beyond known limits. Their experiences directly influenced cockpit design, flight control systems, and training philosophies. The concept of the test pilot evolved from skilled aviator to systems manager, a role that anticipated the demands placed on future astronauts and advanced fighter pilots. As the X-plane program matured, its focus expanded beyond speed and altitude. Engineers began to explore unconventional configurations that challenged the very notion of what an airplane should look like. Lifting bodies, variable sweep wings, and forward-swept wings emerged as solutions to specific aerodynamic problems. These designs were often unstable by nature, impossible to fly safely without electronic assistance. This instability, once seen as a fatal flaw, became a feature. The development of fly-by-wire systems marked another paradigm shift. By replacing mechanical linkages with electronic controls, engineers gained the ability to actively stabilize aircraft that would otherwise be uncontrollable. Experimental platforms like the X-29 demonstrated that forward-swept wings, long dismissed due to structural and aerodynamic challenges, could offer superior maneuverability and lift characteristics when paired with advanced control systems. This research directly influenced modern fighter aircraft, whose agility depends on continuous computer intervention. The socio-economic impact of the X-plane program extended far beyond military applications. Data gathered from experimental flights flowed into civilian aviation, improving safety, efficiency, and performance. Commercial airliners benefited from refined aerodynamic models, more efficient wing designs, and improved understanding of high-altitude flight. These advancements reduced fuel consumption, expanded global air travel, and reshaped international commerce. Faster, safer, and more efficient aircraft connected distant economies, accelerated globalization, and transformed cultural exchange. Equally important was the industrial ecosystem that formed around experimental aviation. The X-plane program demanded close collaboration between government agencies, private aerospace firms, universities, and research institutions. This collaborative model accelerated innovation and cultivated generations of engineers skilled in systems, thinking, and interdisciplinary problem-solving. The technological spillover extended into materials science, computing, propulsion, and control theory, strengthening the broader economy. Culturally, the X-planes captured the imagination of a nation. Though many programs remained classified for years, the idea of aircraft pushing beyond known limits resonated deeply with the public. These machines symbolized curiosity, courage, and the belief that human ingenuity could overcome seemingly insurmountable barriers. They stood as tangible expressions of a society willing to invest in knowledge for its own sake, even when immediate returns were uncertain. As decades passed, the legacy of the X-plane program continued to evolve. Modern experimental aircraft explored quiet supersonic flight, seeking to reduce sonic booms and make high-speed travel socially acceptable over land. Others focused on hypersonic propulsion, blending scramjet technology with reusable airframes. Each new project built upon a foundation laid by earlier experiments, reaffirming the enduring value of incremental, data-driven exploration. In the final analysis, the X-planes were never about a single aircraft or a single achievement. They represented a philosophy of progress grounded in disciplined risk-taking and relentless curiosity. By embracing uncertainty and transforming it into structured experimentation, NASA and its partners redefined the boundaries of flight. The lessons learned in the desert skies did not remain there. They shaped the aircraft that carry millions of passengers each day and the spacecraft that venture beyond Earth. The story of the X-planes is a reminder that the greatest advances in aviation do not come from playing it safe, but from deliberately confronting the unknown with rigor, humility, and resolve. It is a testament to the engineers who designed machines without precedent, the pilots who trusted them with their lives, and the institutions that understood that knowledge itself is a strategic asset. The history of aviation is written not only in steel and composites, but in data, courage, and the will to challenge limits that once seemed absolute. As the experimental philosophy matured, the scope of what an aircraft could be expanded dramatically. The desert test ranges became arenas where engineers no longer asked whether a configuration would work, but what could be learned when it inevitably failed. This mindset transformed engineering culture. Instead of optimizing designs solely for operational readiness, teams optimized for information. Instrumentation grew as important as structure. Telemetry streams became lifelines, transmitting thousands of parameters in real time from aircraft to ground stations, allowing engineers to see the invisible forces acting on wings, fuselages, and control systems. One of the most profound challenges confronted by the X-plane lineage was the problem of stability. Traditional aircraft relied on inherent aerodynamic stability to remain controllable. Designers intentionally built airplanes that naturally returned to straight and level flight when disturbed. But this stability imposed limits on performance. As speeds increased and maneuverability demands intensified, stability became a constraint rather than a safeguard. Engineers began to explore the counterintuitive idea of relaxed static stability, accepting natural instability in exchange for greater agility and efficiency. This approach demanded a technological leap. Human reflexes alone could not respond fast enough to stabilize such aircraft. The solution emerged through digital fly-by-wire systems, which translated pilot inputs into electronic signals interpreted by onboard computers. These computers continuously adjusted control surfaces, making thousands of corrections per second. Experimental aircraft served as the proving ground for these systems, validating algorithms, redundancy strategies, and failure modes under real flight conditions. The implications were profound. Aircraft no longer needed to be naturally stable to be safe. Instead, safety could be engineered through software and systems architecture. This revelation reshaped aerospace design across both military and civilian sectors. Modern fighters owe their extraordinary maneuverability to concepts first validated in experimental programs. Even commercial aircraft adopted fly-by-wire systems to improve efficiency, reduce weight, and enhance safety through envelope protection. Another frontier explored by the X-plane program was the interaction between materials and extreme environments. As aircraft reached hypersonic speeds, aerodynamic heating imposed stresses that conventional aluminum alloys could not endure. Engineers were forced to develop new materials and structural concepts capable of surviving temperatures that softened metals and degraded composites. Nickel alloys, titanium structures, and advanced thermal coatings emerged from this necessity. These innovations extended far beyond aviation. The knowledge gained influenced spacecraft design, industrial manufacturing, and even energy systems. The challenge of managing heat at hypersonic speeds directly informed the development of reusable space vehicles, where thermal protection became a critical factor in mission viability and cost control. Once again, experimental aircraft acted as bridges between theoretical research and practical application. Risk, however, remained an ever-present companion. Test pilots operated at the edge of survivability, often with no margin for error. Their role demanded not only exceptional flying skill, but also deep technical understanding. They were active participants in the engineering process, providing qualitative insights that complemented quantitative data. A vibration felt through the control stick, a hesitation in engine response, or a subtle change in handling could reveal flaws invisible to sensors. The losses endured during these programs underscored the cost of progress. Each accident prompted rigorous investigation, leading to design revisions, procedural changes, and deeper understanding. Rather than halting experimentation, these tragedies reinforced the commitment to learning. Safety improvements were not reactive known fixes, but proactive safeguards grounded in data and systems thinking. As experimental aircraft grew more complex, the scale of collaboration expanded. Universities contributed theoretical research, industry partners developed specialized components, and government agencies coordinated funding and oversight. This ecosystem accelerated innovation while distributing risk. The X-plane program became a model for how large-scale technological challenges could be addressed through coordinated effort rather than isolated competition. Economically, the long-term returns on this investment were substantial. Breakthroughs originating in experimental programs reduced development costs for future aircraft by eliminating uncertainty early in the design process. By understanding aerodynamic behavior, structural limits, and control dynamics before committing to mass production, manufacturers avoided costly redesigns and delays. The resulting efficiency strengthened national competitiveness in a global aerospace market. Beyond economics, the influence of experimental aviation reshaped public perception of flight. Aircraft were no longer viewed solely as transportation tools or weapons, but as embodiments of scientific exploration. Each new record flight captured attention and inspired future generations of engineers and pilots. Educational institutions integrated aerospace research into curricula, feeding a talent pipeline that sustained innovation for decades. As the 20th century progressed, experimental aircraft increasingly addressed environmental and operational concerns. Noise reduction, fuel efficiency, and emissions became central challenges. Programs investigating laminar flow control, advanced propulsion integration, and alternative fuels sought to reconcile performance with sustainability. These efforts acknowledged a changing world where technological advancement had to align with societal expectations and environmental responsibility. The quest for quiet supersonic flight exemplified this shift. Sonic booms, once accepted as unavoidable, were re-examined through the lens of community impact and regulatory constraints. Experimental platforms tested new shaping techniques designed to spread shockwaves and reduce ground-level noise. The goal was not merely to fly faster, but to do so in a way that expanded access rather than imposed costs on society. At the same time, hypersonic research returned to prominence, driven by both strategic and scientific interests. Speeds exceeding Mach 5 introduced challenges that blurred the line between aerodynamics and thermodynamics. Airflow became chemically reactive, and propulsion systems had to operate within narrow windows of pressure and temperature. Experimental aircraft provided the only means to validate models in this regime, where wind tunnels and simulations remained insufficient. Throughout these endeavors, the underlying philosophy remained consistent. Experimental aircraft were tools for disciplined exploration, designed to fail safely, gather data, and inform the next iteration. Success was measured not solely by performance milestones, but by the clarity of understanding achieved. This perspective distinguished the X-plane legacy from conventional development programs driven by immediate operational requirements. The cumulative effect of decades of experimentation reshaped aviation's trajectory. Concepts once considered radical became standard practice. Digital flight controls, advanced materials, and integrated systems architecture moved from experimental prototypes to everyday reality. Air travel grew safer, more efficient, and more accessible, altering patterns of commerce, migration, and cultural exchange on a global scale. In reflecting on this evolution, one truth stands out. The greatest contributions of experimental aircraft were not the machines themselves, but the mindset they cultivated. By embracing uncertainty as an opportunity rather than an obstacle, engineers and pilots expanded the boundaries of what was possible. Each flight represented a question posed to nature, and each data set contributes to an ever-growing body of knowledge. This legacy continues to shape the future of aviation and aerospace. As new challenges emerge, from autonomous flight to sustainable propulsion, the lessons of the experimental era remain relevant. Progress depends not on avoiding risk, but on understanding it, managing it, and learning from it with rigor and humility. The story of experimental flight is, at its core, a story about humanity's enduring desire to explore, to understand, and to push beyond the limits of the known world. As experimental aviation entered a more mature phase, the emphasis shifted from proving that radical ideas could work to understanding how they could be refined, scaled, and integrated into operational systems. The data accumulated from decades of flight testing began to reveal patterns. Engineers could trace direct lines from experimental anomalies to practical solutions. What once appeared as isolated breakthroughs gradually formed a coherent body of knowledge that reshaped aerospace design philosophy. One of the most significant paradigm shifts involved the relationship between pilot and machine. Early experimental aircraft demanded constant vigilance, with pilots actively fighting instability and responding to unpredictable behavior. Over time, control systems evolved from simple stability augmentation to fully integrated flight management architectures. These systems did not merely assist the pilot. They actively shaped the aircraft's behavior, filtering inputs, preventing unsafe maneuvers, and optimizing performance in real time. The aircraft became an intelligent partner rather than a passive tool. This transformation altered how aircraft were certified and flown. Safety was no longer defined solely by mechanical redundancy, but by software reliability and systems integration. Experimental programs validated fault-tolerant architectures, ensuring that no single failure could lead to catastrophic loss of control. These principles migrated into commercial aviation, contributing to the remarkable safety record enjoyed by modern air travel. Passengers rarely consider that the smoothness and predictability of their flights are rooted in lessons learned from aircraft deliberately pushed to their limits decades earlier. The influence of experimental aircraft also extended into propulsion technology. Traditional turbojet and turbofan engines reached diminishing returns as designers sought higher efficiency and lower emissions. Experimental platforms provided a testbed for variable cycle engines, advanced inlet designs, and alternative combustion concepts. These efforts aimed to reconcile competing demands: high thrust for takeoff and climb, efficiency at cruise, and reduced environmental impact. By exploring these trade-offs in flight, engineers gained insights unattainable through static testing alone. At extreme speeds, propulsion and aerodynamics became inseparable. Hypersonic research demonstrated that an aircraft's shape could serve as part of its propulsion system, compressing and accelerating airflow before it entered the engine. Scramjet concepts, once purely theoretical, were brought into reality through experimental flight programs. Though operational hypersonic aircraft remain a challenge, the data gathered established a foundation for future systems capable of traversing vast distances in hours rather than days. The socioeconomic implications of these advancements were far-reaching. Faster and more efficient aircraft reduced travel time, expanded markets, and enabled just-in-time logistics on a global scale. Industries reorganized around the assumption of rapid air transport, from perishable goods to high-value manufacturing. Experimental aviation, though often invisible to the public, quietly underpinned these transformations by de-risking technologies before they entered commercial service. Education and workforce development were equally influenced. Experimental programs demanded engineers fluent in multiple disciplines: aerodynamics, materials science, software, human factors, and systems engineering. This interdisciplinary approach established new standards for engineering education. Universities adapted curricula to reflect the complexity of modern aerospace challenges, producing graduates capable of navigating interconnected systems rather than isolated components. Cultural impact followed naturally. The narrative of experimental flight resonated with a broader story of exploration and innovation. Test pilots became symbols of calculated bravery, embodying a balance between courage and analytical rigor. Their experiences reinforced the idea that progress is not reckless, but deliberate, built on preparation, discipline, and respect for the unknown. This ethos influenced not only aviation but other high-risk fields, from space exploration to advanced medicine. As experimental aircraft explored new configurations, the concept of efficiency evolved beyond speed and altitude. Designers began to consider life cycle costs, maintainability, and adaptability. Aircraft were evaluated not just on peak performance, but on how easily they could be upgraded, repaired, or repurposed. This systems-level thinking reduced long-term costs and increased resilience in an industry characterized by rapid technological change. Environmental considerations gained prominence as well. The realization that aviation's growth carried ecological consequences prompted experimental programs focused on sustainability. Laminar flow wings reduced drag and fuel burn. Lightweight composite structures improved efficiency. Alternative fuels were tested to assess compatibility with existing engines and infrastructure. These efforts reflected a broader understanding that technological leadership must align with societal responsibility. Experimental aircraft also played a role in redefining national strategy. Control of advanced aerospace technology became a measure of geopolitical influence. Nations capable of developing and testing cutting-edge aircraft signaled not only military strength, but scientific and industrial maturity. The collaborative frameworks established during earlier experimental programs provided a blueprint for international partnerships, balancing competition with shared progress. Over time, the boundary between experimental and operational aircraft blurred. Many features once considered experimental became standard equipment. Digital flight controls, composite airframes, and advanced avionics transitioned seamlessly into production models. This integration shortened development cycles and reduced uncertainty, enabling manufacturers to innovate more rapidly without sacrificing safety. Perhaps the most enduring contribution of experimental aviation lies in its methodology. The iterative process of hypothesis, test, analysis, and refinement created a feedback loop that accelerated learning. Failures were not endpoints, but data points, informing the next design iteration. This mindset fostered resilience and adaptability, qualities essential for navigating complex technological landscapes. As the aerospace community looks toward emerging challenges, from autonomous systems to spaceplane concepts, the lessons of experimental flight remain indispensable. Autonomy introduces questions of trust, accountability, and human-machine interaction. Experimental platforms provide a controlled environment to explore these issues before widespread deployment. Similarly, reusable launch vehicles draw heavily on knowledge gained from high-speed atmospheric flight and thermal management research. The story of experimental aviation demonstrates that true innovation is rarely linear. It unfolds through cycles of exploration, uncertainty, and discovery. Each generation builds upon the foundations laid by those who came before, extending reach while refining understanding. Experimental aircraft, though few in number, have exerted an influence disproportionate to their scale, shaping an entire industry and redefining humanity's relationship with flight. In the broader arc of history, these machines represent more than technological artifacts. They embody a philosophy that values knowledge over immediate utility, preparation over improvisation, and learning over complacency. By daring to fly where theory ends, experimental aviation transformed the unknown into the understood, ensuring that the skies remain not a barrier, but a pathway to progress. By the time experimental aviation reached its later stages, its influence had become so deeply embedded in aerospace design that it was often invisible. Aircraft rolling off production lines carried within them decades of experimental knowledge, encoded into software logic, structural layouts, and aerodynamic shaping. What had once been daring test concepts were now assumptions, quietly enabling performance levels that earlier generations could scarcely imagine. One of the most significant evolutions was the way engineers approached uncertainty itself. Early experimental programs treated unknowns as discrete problems to be solved one at a time. Later efforts recognized that uncertainty was systemic, emerging from the interaction of multiple variables operating simultaneously. This realization drove the adoption of integrated modeling and simulation environments, validated by flight test data. Experimental aircraft became the final arbiters of truth, confirming or challenging predictions generated by increasingly sophisticated computational tools. This synergy between simulation and flight testing transformed development timelines. Designers could explore thousands of configurations digitally, narrowing options before committing to physical prototypes. Experimental aircraft then verified critical assumptions, reducing risk before large-scale investment. The result was a more agile aerospace industry, capable of responding to changing requirements and emerging threats without sacrificing safety or reliability. The legacy of experimental flight also reshaped how human factors were understood. As aircraft systems grew more complex, the role of the pilot evolved once again. Rather than directly controlling every aspect of flight, pilots increasingly supervised automated systems, intervening only when necessary. Experimental platforms explored this balance, testing interface designs, workload management strategies, and alerting systems under extreme conditions. These insights informed cockpit layouts and automation philosophies that emphasized clarity, redundancy, and trust. This research proved essential as automation expanded beyond assistance into autonomy. Experimental aircraft evaluated decision-making algorithms, sensor fusion techniques, and fail-safe behaviors in dynamic environments. The goal was not to replace human judgment, but to augment it, ensuring that machines could handle routine tasks while humans focused on strategic oversight. This partnership between human and machine became a defining feature of modern aviation. Beyond the cockpit, experimental aviation influenced manufacturing itself. Advanced materials introduced new production challenges, from precision fabrication to quality assurance. Experimental programs tested not only performance, but manufacturability, maintainability, and repairability. The lessons learned reduced life cycle costs and improved durability, making advanced technologies economically viable at scale. The ripple effects extended into global infrastructure. Airports adapted to accommodate new aircraft capabilities, from longer runways for high-performance jets to quieter operations that reduced community impact. Regulatory frameworks evolved alongside technology, informed by empirical data gathered during experimental flights. Policymakers gained confidence to approve new designs because those designs rested on a foundation of rigorous testing and transparent analysis. Culturally, the narrative surrounding experimental aviation matured. Early achievements were framed as feats of daring and individual heroism. Over time, the emphasis shifted toward collective expertise and institutional learning. Success was understood as the product of interdisciplinary collaboration, meticulous planning, and relentless iteration. This perspective reinforced public trust in aviation as a domain governed by evidence rather than bravado. Internationally, experimental aviation became a quiet instrument of diplomacy and influence. Cooperative research programs fostered knowledge exchange, aligning standards and reducing duplication of effort. Even amid geopolitical competition, shared technical challenges encouraged collaboration, particularly in areas such as safety and environmental impact. The skies became a space where rivalry coexisted with mutual dependence. As experimental programs continued, their focus increasingly aligned with future-oriented challenges. Climate considerations, urban air mobility, and integration with space operations emerged as priorities. Experimental aircraft evaluated distributed propulsion, electric powertrains, and hybrid systems, probing their feasibility under real-world conditions. Though many concepts remained developmental, the data gathered informed policy decisions and investment strategies shaping the next era of flight. The influence of experimental aviation also extended into public imagination in subtler ways. Educational outreach, museum exhibits, and archival releases revealed the stories behind once-secret programs. These narratives inspired new generations to pursue careers in science and engineering, sustaining the talent pipeline essential for continued innovation. The experimental aircraft themselves became artifacts of progress, symbols of a period when exploration was driven by disciplined curiosity. As technologies matured, the distinction between experimental and operational platforms continued to blur. Incremental upgrades replaced dramatic leaps, guided by continuous testing and feedback. This evolutionary approach reduced disruption while maintaining momentum, ensuring that innovation remained steady rather than sporadic. Looking back, the cumulative impact of experimental aviation defies simple measurement. Its contributions are woven into every aspect of modern flight, from the algorithms stabilizing aircraft to the materials shaping their skins. The program's true achievement lies not in any single milestone, but in the creation of a sustainable process for discovery. In this sense, experimental aviation represents a long-term investment in understanding. It acknowledges that progress emerges not from certainty, but from the disciplined exploration of uncertainty. By repeatedly confronting the unknown and converting it into knowledge, experimental aircraft ensured that aviation would continue to advance without losing sight of safety, responsibility, and purpose. As the aerospace community prepares for challenges that will define the coming decades, the lessons of experimental flight remain a guiding force. They remind us that innovation is not an event, but a continuum sustained by curiosity, rigor, and the willingness to learn from every flight, whether triumphant or flawed. In the final balance, The story of experimental aviation is not defined by the silhouettes of unusual aircraft or by records etched into history books. It is defined by a deeper achievement, the transformation of uncertainty into structured knowledge. Every experimental flight represented a deliberate step into the unknown, guided not by recklessness, but by preparation, instrumentation, and analysis. Each data point collected in those remote skies became part of a cumulative understanding that reshaped how humanity designs, flies, and trusts machines that move through the air. The legacy of experimental aircraft lies in their ability to collapse the distance between theory and reality. Wind tunnels, simulations, and equations provide insight, but flight reveals truth. Experimental programs acknowledge this fundamental reality and built an entire philosophy around it. Rather than waiting for perfect certainty, engineers accepted that some answers could only be found by flying. This acceptance accelerated progress across generations, allowing aviation to advance at a pace that would have been impossible through conservative development alone. The socioeconomic consequences of this approach continue to ripple outward. Global air travel, once a luxury, became a cornerstone of modern civilization. Supply chains spanning continents depend on reliable, efficient aircraft. Entire industries, from tourism to high-technology manufacturing, are structured around assumptions made possible by advances born in experimental programs. Though passengers may never see an X-plane, they live in a world shaped by its influence. Equally enduring is the cultural impact. Experimental aviation reframed how societies perceive risk and innovation. It demonstrated that progress does not require blind leaps, but informed ones. That complex problems can be addressed not through singular genius, but through disciplined collaboration. Engineers, pilots, analysts, and policymakers learned to speak a common language grounded in evidence and systems thinking. This mindset extended beyond aviation, influencing how other fields approach exploration, from spaceflight to autonomous systems. As the aerospace horizon expands toward autonomous flight, sustainable propulsion, and integration with space operations, the experimental tradition remains indispensable. New challenges will bring new unknowns, just as supersonic and hypersonic flight once did. The tools may evolve, becoming more digital and more automated, but the core principle endures. Progress demands environments where ideas can be tested honestly, where failure is analyzed rather than hidden, and where learning is valued above immediate success. In this continuity, experimental aircraft stand as quiet sentinels of human ambition. They are reminders that the most important advances often occur far from public view, in controlled risks taken by people who understand that knowledge itself is a strategic resource. Their flights were not spectacles, but questions posed to nature and answered through data, analysis, and iteration. The history of experimental aviation shows that the sky has never been a fixed boundary. It is a dynamic frontier, reshaped by curiosity and discipline. From the first tentative ventures into supersonic flight to the exploration of hypersonic regimes and beyond, each generation has extended what is possible by standing on the insights of those who flew before them. In the end, experimental aircraft did more than expand the flight envelope. They expanded humanity's confidence in its ability to understand and shape complex systems. They proved that ambition, when paired with rigor, can turn the unknown into the routine and the impossible into the expected. The story they leave behind is not merely one of speed, altitude, or technology, but of a method for progress itself. The history of aviation is written with steel, ingenuity, and the will to challenge limits. Experimental flight is where that history finds its clearest expression, a testament to the enduring belief that the boundaries of today exist only to be explored, understood, and ultimately surpassed.